Actually, I found it useful as well. Anyway, this is very good.
You know how to
Yeah, that's cool. Well, good afternoon. I hope you're surviving the first day of the full show, and you're still going at 3:30. That's very good. Very impressed. So, talking of tea, just one little plug. I do try and do a regular podcast, roughly once a month, on a technology topic. So, if you check out with your usual podcast provider, check out Time for Tea, and you'll find that. And I'll get back to the tea offer at the end of the session. For those of you that are with me this morning in the session, I'm just going to repeat the first 3 or 4 slides just to give some context. Then we're going to jump in to the specifics of this afternoon. So, the live production workflow. This is obviously a very straightforward. What I'm talking about very specifically in this session is that live production workflow, from the acquisition site through to the various elements of the content production processing through to emission. And one of the big observations of where we have moved to as an industry is distributed production is here to stay. And what I mean by that is it's now no longer the top model there, with the acquisition being co-located with the processing and storage being co-located with the control. That's how everything was done until probably 10 years ago, and then helpfully accelerated by COVID. But many people were moving that way anyway. We've embraced a whole load of other models of the way we do distributed production, and this has great benefits. It has great benefits because we can use our staff more efficiently if they're not having to travel. We can actually use our equipment, our actual processing resources more quickly, more efficiently if they can be reused more creatively and more fully. And also there are some other elements. Obviously, there's a sustainability angle. There's also an accessibility angle, because if the people that are operating stuff don't need to be climbing into trucks in the backs of car parks at events and can actually be in a well-provided facility somewhere else, that makes things more accessible. So there's a whole load of benefits there. And more, as we're going to get to later on, more and more of the processing and storage is in that bottom model is in cloud, be that private data center or public compute. So that's kind of a principle which underlies and underpins some of what we're going to be talking about now. And just another trend of the industry that I think is very important is the genericity, I think that's a word, we're embracing as an industry more and more. So our connectivity, we're moving from beloved XLR connectors and BNCs to Ethernet connectors. That physical layer, which we used to work so hard on in terms of the pristine clock on AES interfaces, or the eye on the SDI, or the HD SDI, or the 3 gig SDI, or unbelievably the 12 gig SDI interface. It's now a thing of the past because we're abstracted from that physical layer of connectivity. Virtualization, moving from machines that do specific things, and you've heard a lot of that today in many talks, to compute that's actually realizing those functions for us. Dematerialization, term copyright by Felix Poulon from the CBC, where we're actually, the processing we want to have done isn't even necessarily done where we are. It's done somewhere else, going back to that last picture I showed you. And then networking. I think this is a really important one, and this applies to what we're going to be talking about in a minute. In broadcast production, until relatively recently, all connectivity was the preserve of expensive private wires that people hired. Now, more and more, public internet connectivity is being used to provide that, as is low Earth orbit satellite, as is 5G infrastructure. Now, all of them come with challenges and limitations and risks that you don't necessarily have with very expensive private wires. But if they are 1/100th, or in some cases 1,000th of the cost for you, then actually it's a risk that may well be worth taking in lots of opportunities. But it does have prerequisites in terms of how you need to handle that. Thinking of like long distance production, which we are effectively in this conversation this afternoon, the only non-negotiable that we have in terms of how to make things work is the speed of light and fiber. Everything else is within our gift to engineer how we want to do something, but this has some specific limitations in terms of the way we can do some things, and it puts some constraints, but actually I would argue a lot of the constraints are created by us in the choices of how we implement things rather than the speed of light and fiber. The speed of light and fiber, you can actually go a long way very fast. But some of these elements here, etc., and you'll see I've got a thing about buffers. I'm going to come back to that in a minute. You can actually introduce a lot of unnecessary latency in the requirements. Okay, so typical. Someone's very excited out there, aren't they? It's obviously we've not quite got that energy in here yet. But by the way, I would like to commend James for that previous presentation. If you're watching online, go back and check it. Because a good use of 2110-41, and there is other requirements for metadata, end-to-end metadata that need to be adopting 2110-41. So do check that out, and I will encourage people that are actually interested in real-time, timely metadata propagating in a production workflow to do look at embracing -41 to carry that stuff. But sorry, I just meant to say that when I started up. So this is typically an example, a non-exhaustive list of what you may want to be transporting when you're doing a true REMI. Now, the term REMI was in discussion at the SVG event yesterday. I think most people actually call it different things. There's at-home production, there's REMI, distributed production, whatever you call it. It's this concept of actually having the acquisition location elsewhere from where you're actually doing processing and control. And these are typically some of the things that we want to be carrying, and we're going to come on to the latency question in a minute, which applies to both the audio and the video and other things in terms of what's the criticality of that, and the criticality of the latency does impact the choices of technology we make. So as an example, I used the delay, the latency picture previously, talked about ARQ being a significant increaser potentially of latency, because you're doing at least a whole round trip time to retransmit stuff. Now that may or may not be problems in some elements, and there are different elements of these feeds, which we'll come on to in a minute, that have different requirements in terms of the speed of processing or the absolute latency that we can tolerate. Again, just a picture that I put up this morning of the human ear and the human eye. I think every time I think about how we view stuff and how we hear stuff, I'm just amazed at how amazing our human visual and hearing systems are. And a lot of the tools that we use in broadcasting, we do some tricking of these. The way, ever since television began, in fact, ever since moving pictures began, we've been using the trickery of understanding our human psychovisual system to work out how we can trick it, how we can work, what we can get away with, that our eyes will still see as moving pictures, etc. And similarly with effectively subband compression in audio compression, we know the way we can actually trick what we can tolerate as humans. But the human hearing has acuity, which means that we've actually got some really tight constraints. One thing of that is if we're trying to create a sound field, phase coherency has to be absolutely sample accurate. It's amazing how sensitive the human ear is to phase differences. So phase coherency is something we're going to come back to in a minute when I talk about some connectivity. The other area that's really important, which again we can get away with video that we can't go with audio, is actually the loop back, if you like, of audio queuing, which just simply cannot go long distance, even with the speed of light and fiber. That has to be a local distance thing because of the very, very tight requirements there are. And I've just put on the left there, obviously, a 5.1 surround sound, because all of those audios obviously need to be locked and phase coherent. And another little picture that I put up this morning, and what I just really want to talk about here again is just because it will relate to what I'm coming to in a minute, is there are lots of different tolerable latencies that we have. So there are some things where the closed loop of latency in a live production is really, really important. So actually, obviously, being able to cue the cameramen and women to actually take the shots you want, the tally light being quick enough for them to understand when their camera is actually live on program. There are some other things which are very non-critical, but we actually create with real criticality. So if you think about all the camera feeds for a live production, maybe you've got 18 cameras on a big production. Probably half a dozen of them, 6 of them or even less, are actually being used for the live switch program feed. A lot of the others are beauty shots or they're alternative angles which will only be used on replay. So of the criticality of latency, probably only 6 feeds need to be uber quick. All of the others, we can actually tolerate quite a lot of additional latency because that's really not critical. There's another thing about latency in live production in general, be that the audio or the video control, and that's consistency of latency. Operators are always saying, I can actually, my team can actually learn to cope with a degree of latency in terms of pushing buttons and things happening, or pushing faders and things happening. But if that's variable, then that's intolerable. So deterministic latency what is better than variably, sometimes low-speed latency. So bulk audio transport, what we're now moving to with remote production in general is wanting to backhaul long distance all of the ISO camera feeds, all of the individual audio microphones, etc. So we can do all of our mixing and all of our program production centrally. So there's a number of different ways people are doing that. We may be doing that with native AES24 feeds, and could be everything from individual mono channels to bouquets of 64 brackets, possibly even more channels on single IP flows. And we'll come back to the phase coherency in a minute. MADI has had an amazing resurgence that I've seen in the last few years, simply because it's a deterministic way. There's not some clocking challenges, and I'm going to talk about the clocking in a minute. It's a way of bulk handing off with forward clocking a whole load of audio channels, which is very, very good for remotes. A lot of people are still doing embedded, and obviously on HDSTI you can embed 16 channels, and theoretically, although not many people are doing it, you can do 32 channels of embedded on a 3 gig SDI feed, so you can get quite a lot of audio through there. And then the video, we actually carry in a number of different places, but I want to unpack this a little bit more, and you may be saying, or maybe you haven't been saying, I wonder why some of them are red and I wonder why some of them are green. And the reason is because of the timing models that we need to have between the remote production, the acquisition location, and the central production. So traditionally, what we've had is most remote venue locations for live production have been considered kind of an asynchronous source. So everything about the way you've handed the feeds down the system into your production center is you've actually said, okay, I'm accepting these are coming into me asynchronously. At some point, I'm going to go through a frame sync, or if it's all digital audio, a sample rate converter to get me into my house reference for my timing for my production. But what we have done recently in the advent of 2110 is introduced the concept that actually we can do, if we can guarantee frequency lock, we can actually do things like AES24 and all of the 2110 video feeds remotely and do them with timing reference. So the ones in green here are effectively, as they stand without being protected and having workarounds, are things that assume you've got timing end to end. Now, that's because most of these green things have been designed for in a facility. So in a facility, you've actually got timing references for everything, and that's the way we've done broadcast for many, many, many decades. We've got a common reference. It used to be Genlock, it's now PTP most of the time, and that's how we co-time things. But from these remote venues, as we've moved, we've done quite a lot. I've been involved in quite a lot of deployments between broadcast centers where you've got a GNSS reference. So you actually can rely on the fact you've got stable frequency lock at each end. And you can then do decent AES67/-30, and you can do all the 2110-20 stuff, and it will work. You've got a constant phase offset, so you've got a buffer, and obviously you've got some alignment things there, but it's a static function, and you can tolerate that. A lot of what we face, though, and this is a challenge for people, is when we've got a broadcasting a remote location. Some people use the example of Wembley Stadium in the UK. I don't know whether this is still the case, but you used to, when you drive the trucks in, they're underground. so you can't see the sky, so you can't do an implicit GNSS reference. So you may have a very nice high precision oscillator in your system, but you're not absolutely frequency locked as you're coming through. So you can't rely on the different elements. And I'll explain that a little bit more on the other side. But the beauty of something like AES10 MADI and embedded audio in HDSDI is that actually you're creating that, you're sending it out, and the problem of synchronizing it is inherently downstream. You haven't got to worry that you, as the transmitter, have got a specific timing reference for you to be able to do that. And you can disseminate that, and implicitly you're likely to have sample rate conversion happening downstream on MADI as it hits your PTP locked system. And similarly, you're probably going to go through a frame store and the requisite sample rate conversion on your SDIs as they enter. I also want to point out from the video perspective with relation to the audio, the specific difference between TR07 and TR08, which are becoming almost the ubiquitous ways of doing high quality OBs from the video side for remotes. These are both packing versions of JPEG XS. So again, if you're not familiar, we have uncompressed video, which is actually the best. If you don't compress if you don't have to, is the general rule in life. But in general, bandwidth is a little bit more precious than that, especially from the video side. So we want to compress the video. And JPEG 2000 has been around for 15 years now, had become the kind of default mezzanine compression, roughly a compression ratio of 8:1, 10:1. JPEG XS is a derivation of that with even lower latency. So JPEG XS, the big selling point of it is it's a sub-millisecond compress-decompress. So once you're routing long haul on fiber, then the compression is effectively negligible. You've not got any cost there. So we're tending to use JPEG XS quite a lot. Obviously, if you're bandwidth challenged, if you've got a 1 gig circuit rather than a 10 gig circuit, then you're going to be wanting to use HEVC or AVC because for all your ISO videos, because that's the only way you're going to get them in the bandwidth. But TR07 and TR08 are both ways of carrying JPEG XS. TR07 wraps it in a transport stream. And traditionally, it's a very high bitrate transport stream compared with what you may be used to. Nobody, I think, ever thought a transport stream might have more than a gigabit per second in it a few years ago. But that's what we're delivering now if we're doing UHD in TS. But TR07 means that we can do that same adaptive clock recovery at the back end and do all the usual processes to synchronize that in. So TR07 is inherently what I call a forward clocking mechanism, and we don't have to rely on the remote being synchronous to actually make that work. TR08, on the other hand, which I am passionate about because I helped kind of evolve that as well, assumes that you've got synchronicity because it's effectively part of the 2110 suite. It's 2110-22, and we are actually encapsulating the -20, the PCM video, into XS, and we're carrying it, but it's the mechanisms of 2110 are assuming a timing reference for that. So that's why we've got the green and the red between those. And obviously, just goes without saying that 2022-2, that is transport stream over IP, and 2022-6 is a forward clocking alternative. It's effectively the original packetized SDI into IP that was a precursor to 2110. So that's a little bit of derivation of the timing. And I think I've probably brought us through this, but this is just to bring it out like there. The PTP, where we've actually, we need to know the source and the destination. They need to be frequency synchronous for actually us to do that equivalent of the link offset recovery and presentation. Whereas if we have an adaptive solution, then the decapsulation itself is actually working out the buffer management it needs to do to recover the audio to be able to present it. Next comes a question on audio compression. And again, my premise stands with video and audio. If you don't need to compress it, don't. It's much better to leave it uncompressed. But interestingly, we do see some scenarios where people ask the question about compression. And I think it really depends on the order of magnitude of bandwidth you've got. So just trying to go there. So uncompressed, by the time you've encapsulated an IP, a stereo pair of audio at 48 kilohertz, 24-bit is roughly 3.5 megabits per second. So that means if I'm carrying 64 channels like a MADI's worth or an AES27 64 channel worth, It's the order of 120 megabits per second for me to carry that through. Now, that may or may not be seen as quite a costly bandwidth, depending on what else you're doing. If I'm actually carrying a whole load of JPEG XSs, so I'm carrying some 1080p videos, then if I've got 12 of them, 12 ISOs on the camera, 4 gigabits per second, then carrying 120 megabits per second of audio is a triviality, probably. If, however, I'm in a really constrained environment, then, and I'm trying to do it with maybe even 100 megabits per second link and do a much more smaller production, then maybe I need to consider some compression. But in general, it's possible to do it, and we can use like the traditional compression that we use alongside video that most of our compression engines are used to, or there's other standalone lossless and nearly lossless audio compressions we can use to make that, but I'm not going to dive into that. In terms of how many audios do we carry within each feed, I actually know a deployment of a 2110 deployment where, to keep audio routing flexibility and to be able to shuffle on demand in the IP domain, they actually made the decision to do all mono. So it's all mono routing in the facility. And theoretically, and in most practical circumstances, that actually works brilliantly because PTP absolutely gives us sample accurate behavior. However, what I would say is, in general, the best practice I've seen for most people is to actually respect phase coherency within a transport, within a single channel. So if you're carrying stereo, carry it as a stereo. If you're carrying 5.1 or any other surround, carry a channel bandwidth that's enough. So the IP flow you're carrying, has actually got all the critical phase coherent material within it. There are exceptions to that. That's just an observation of de-risking and best practice. So in the US, when I've been talking to customers, they use the term normalization. Normalization for me is actually about controlling the amplitude of an audio signal to actually make it, is it the right loudness effectively between flows and between parts of an audio stream. But normalization in the general term that we see from our customers is actually pulling things together. And there is a similar thing for a video normalization, which we have as well, in terms of the temporal and spatial resolution, the HDR behavior, all of those things that on the video side. But we see an awful lot of requirements to be able to do these kind of manipulations as part of the processing to getting to handoff, because a lot of downstream equipment, once you get into it, doesn't necessarily have the flexibility of being able to support any number of channels per audio stream, or have limitations on the packet period of the sampling, etc., and not being able to potentially do the shuffling and manipulation that you need. So these are key tools available. I talked about protection. Again, just want to say this again, mainly from a latency perspective. So 2022-7 has just been amazing. We did one of the first implementations in my previous company back in 2010, I think. And it just seems such a good thing to do. And the great thing about 2022-7, it's a diverse RTP transport. You have some kind of spatial diversity. You can do this within a plant, within a facility, or on long distance transport. And you just merge the flows at the other end. And literally, the only cost of doing that, well, there are two costs. There's a significant cost because you've got double bandwidth. So assuming you've got that double bandwidth, the only cost is normalizing the shortest path to be long enough to meet the longest path, and you've got very, very comprehensive protection. 5 minutes. I've got my 5-minute warning. FEC can actually be quite a low latency way of protecting services. And then there's ARQ, which I talked about, and I want to raise it because many people are using ARQ on everything, both on public internet connectivity, which is very understandable because of the lack of determinism of the integrity, but also people are starting to use it on private wire as well, which I have to say, from a technical perspective, I really don't understand, because if you don't need to, that's the most costly, because ARQ, you at least need a round trip time to compensate, and actually if you do a recursive or iterative ARQ, you could actually have multiple round trip times. So suddenly that protection can become very, very costly. I'm just going to jump through one or two of these bits. I just want to say, oh no, I will just show this briefly. I will just show this previously briefly. One of the things that's happening as we move more of our live production processing into software is where we're actually moving to that being an asynchronous function. So previously we've had this for many years, what I call this hose pipe. So everything in video and audio has been this linear transport, even from analog through to all of the digital incarnations, up to and including AES24 and 2110, of still constant flows of bits. And as we move into doing more and more of this stuff in compute doesn't do linear streams. Compute just takes stuff, handles it, and dumps it. And see my presentation from this morning, because I'm just going to rattle through this because we're running out of time. But it's very important that timestamping is honoured as we move into this new area. We've got away without doing much timestamp management of data up until now, because it's been in the serial pipe and we can do lots of things just by the equivalence of the time or when stuff arrives. As we move into an asynchronous world, we're much, much less able to do that. So as we move to compute workflows, we need to be very, very careful about timestamp management. Just want to shout out to 3 initiatives in the production space that are happening. There's this GCCG work that I'm involved in, and specifically the cloud-to-cloud bit we're now prototyping, which is this asynchronous handoff with timestamping of media data, be that video and audio. Also, a shout out, the BBC have recently talked about TAMS, which is a time addressable media store, and basically this is a potentially latency incurring, but it is actually a technique, and that the latency would be definable within the architecture that you do this. But it's all about moving. There's a convergence of production and post-production, and being able to do editing as well as live production. The work on the right from the EBU, again recently launched, is all about the framework in which we need to do this compute exchange. And a little bit of an explainer here. Again, see this morning's video for more details between signal-centric workflows and storage-centric workflows. We haven't got time to unpack. I'm going to give a little plug for some work I'm doing on Essence alignment, which we're still trying to draw to a conclusion. And Andreas is helping us on this sometimes as well. Trying to actually get the end-to-end chain of alignment, because the great thing about separating the audio and video out is you don't have to worry about each other till you converge. But at the point you converge, you need to know what the relative offsets of the timing is, or else you've got lots of challenges. So this is my concluding slide. I don't need to go through it, apart from just to remind you that actually the audio is the most important bit of a production at the bottom. So these are some of the things we've covered. Hopefully it's triggered some thoughts. I'd love to talk to you further, and I'd like to invite you either on our booth the next day, or back in the UK, or whenever I next see you, for a nice cup of tea.